Hi guys. I thought, well, I've had some requests on getting back to doing some theory videos. Now I am still working on the Admiral, so, and there will be videos coming up on it, so don't worry about that series. Very soon I'll be doing another video on it, but I wanted to get a couple videos out of the way. We're going to start off with one that's been requested, and it's been requested by a few people, and that's talking about a term called impedance. And in the simplest terms, impedance is nothing but AC resistance. But how do you figure it, and what does it really mean, and what is it used for? And a lot of students in school will have troubles with this. It's a real difficult concept at first to get a grasp on and to understand, partially probably because of its name and also a few other little factors. Now, to give just a tad bit background of what generally happens if you was to go to school, to a tech school or junior college or anything of that nature, to learn electronics and electricity, the very first thing that they teach you is DC circuits, primarily because they're simple to understand. You only have really basically two things in the circuit. You have a power source, generally a battery, gives you a pure DC, and a load, which is generally just a resistor or number of resistors. And through the DC course, they'll teach you some stuff that you're going to need all the way through electronics and working with electronics, things such as Ohm's law, which is highly important, and it's a lot easier to work with or for you to understand than taking you right into AC if we just do DC, because you only have two things you're looking at, and then that's your power source and a load or resistance. So it's easy to teach Ohm's law there. And they take you through a lot of other stuff about dealing with various different resistor combinations in series and parallel, and Kirchhoff's laws, and various different information of circuits, what a circuit is, how the current's broken up in different branches, and so forth. Then you go into AC, and when you get in AC, you start learning about other components. First you study about what an AC is, and then you go into capacitors and inductors, inductive reactance, capacitive reactance, and of course AC circuits also have resistors as well. And everything's measured in ohms, and it gets rather confusing, and then they throw impedance at you and it's measured in ohms. So before going directly into impedance, we got to go and show you how it's figured. The first thing you need to do is do a little preliminary math review, or maybe for some of you it may be something new. In school, and I'm not going to use my black marker because it's about done for, so I'll probably use blue. In school, in geometry, and a lot of times this also shows up in either a beginning course in algebra, or at least regular math further down the line. You learn how to solve right triangles. And what is a right triangle? Well, a right triangle is a triangle that's got a 90-degree angle in it, right here. And to make up the rest of the triangle, we have another side. Now this side is always called the hypotenuse, denoted by small h. You can also call it side C, and this side A, and this side B. Now, many years ago, a few thousand now, a Greek named Pythagoras figured out how to solve this triangle. Mainly, if I know two sides, how I can find the third side. And it's called the Pythagorean theorem. And basically what it is, and what it boils down to is a squared, this side, plus b squared, this side, equals c squared, which is the hypotenuse. Another way of writing this, because c squared means nothing, it's not going to be the exact measurement, it's the size of that, or length of that side squared. So another way of writing it would be like this: a squared plus b squared will equal c if we square root this entity here. Now, do a little example, an example that carpenters and builders has used for ages. If I give A 3 units and I give B 4 units, then I can find C. So if we do that, if I take the square root, A is 3, so A squared be 3 squared, plus B, which is 4, is 4 squared, is going to equal my C. Now if I move over here a little bit, we continue with that. 3 squared is 9, 4 squared is 16, and that will equal our C. So add those two together, I have 25 equals C. Take the square root of 25, and C equals 5. Now that can be 30, 40, and 50. It can be 300, 400, and 500. It doesn't matter. Now, but that's the Pythagorean theorem. A squared plus b squared equals c squared. It allows you to solve for a right triangle. And we'll be using this when we solve impedance. And you'll see in a little bit. Now, one other little thing, and I'm just going to touch on it. We're going to be using something called a vector. And I just want to define it more than anything else. I'm not going to get into teaching about vectors on this video. That's something that really needs its own video or series of videos, or at least one good video anyway. But vector. A vector will be represented by a line with an arrow. Now what does it mean? Well, let's use a simple example. If you're, say, driving your car down a road somewhere, matters not where, and if I start asking about information about you driving that car, one thing I can ask you is your speed. And you could tell me you're doing 60 miles an hour. Well, speed is just what is known as a magnitude. it just tells me the speed of the vehicle, or or a size of something, or a dimension. It's just a magnitude, but it's not a vector. It doesn't give me any other information. If I continue quizzing you and you end up giving me up information saying I'm going 60 miles an hour due north, now I have a vector. Because a vector is nothing but a magnitude, the speed in this case, 60 miles an hour, and a direction, which is due north. And that's all a vector is. It gives magnitude. In this case, our magnitude would be 60 miles per hour, and a direction, north. It could be any direction or anything. Another way of emphasizing this is to graph on a graph. In this case, this would be east, this would be north, this would be south, this would be west. And we would have our magnitude along these lines. But if I, numbered off, in this case 60 miles an hour would be this vector right here, with an angle off from east of 90 degrees. So another thing I could say is 60 miles an hour at 90 degrees. All angles on graphs like this are measured as positive angles going counterclockwise. If it was west, it'd be 180 degrees. South would be 270 degrees. And east can be represented either by 0 or 360. But that's as much as I want to deal with vectors, is just what they are. They're just an arrow or a line to represent, or a line with an arrow to represent a magnitude. It can be a speed, it can be a voltage, 10 volts, it can be a weight, 10 pounds, or anything. It's just magnitude and direction. And generally it's done, direction is done with angles as opposed to, such as in this case, example of saying north. Alright, now a few other little things to get by before we actually get to impedance. Impedance, we're going to be using certain, to solve it, certain dimensions, and those basically are inductive reactance and capacitive reactance and resistance. Okay, resistance is easy enough. Resistance is just that, resistance, measured in ohms, and it can be a resistance of a wire, of a coil, or a resistor. So inductive reactance, I wanted to do a review on. I've already wrote these down once before in other videos. Is 2 pi frequency times inductance. Frequency is measured, and this formula is measured in hertz or cycles per second. Inductance will be measured in henries. And capacitive reactance, X sub C, is 1 over 2 pi F, frequency, times capacitance. Again, frequency in hertz, capacitance, and farads. One thing I want to point out is something about these formulas. And that is simply the fact that inductive reactance, the frequency and the inductance is directly proportional to the reactance. In other words, there's a direct connection. If frequency goes up, inductive reactance goes up. If your henries go up, your inductance go up, so does your inductive reactance. Excuse me. But on capacitive reactance, it's indirectly proportional. It's the opposite. If frequency goes up, capacitive reactance goes down. If capacitance go up, capacitive reactance goes down. So if either of these or both go up, this goes down. But inductive, if either one of these or both go up, this goes up. Of course, 2 pi is just a constant, so it never changes. But it's important to note this relationship here and here, as you will see that here pretty soon. Now, first we're going to look at an RL circuit, meaning a circuit that has an inductor and a resistor in it. Matters not whether they're in parallel or they're in series with each other. We're looking for the impedance. When I look at that, I can actually graph it out using vectors. Now this here is X sub L, and this here is R. Now one other thing, X sub L, X sub C, in other words inductive and capacitive reactance, is measured in ohms. So its dimension is ohms. And of course resistance, a resistor is ohms. Now if I have a certain amount, and we'll denote that with an arrow, of inductive reactance, it matters not what size at this point, and a certain amount of capacitive reactance, the impedance is this. It's a line that goes up and intersects a point that these two make. Now the variable used for, or the sign used for impedance is a Z. You know, always put a little line through it just to make sure you don't know it's a 2 or something else. But if I draw a straight line up and I draw a horizontal line across here, this point to a point here, then that will create a vector for impedance. This line up or this line over, either one of these two create a 90-degree angle. I have a right triangle. This line represents the inductive reactance. This line is representative resistance. Since I have a right triangle and then an impedance is the hypotenuse or side C, then I can use the Pythagorean theorem to actually figure it. So basically, going back to the Pythagorean theorem, a squared plus b squared equals c squared. If I can draw. Then I can just substitute these into here. A squared x sub L squared plus b squared, which I can represent as R, equals c, which is z squared. Or, taking the square root of both sides, X sub L squared plus R squared for resistance equals Z. Everything's in ohms. When you plug numbers in here and you do the math, you'll come out with impedance and just in ohms. Now if I go back to the 3, 4, 5 triangle, I could say that I have 3 ohms here, 4 ohms resistance. Now that can be either way. Then impedance must be 5 ohms. Again, it'd be just 3 squared plus 4 squared. Take the square root of that. Gives you this. That's just 25 square root, which equals 5 ohms for my impedance. That's all there is to actually figuring impedance in an RL circuit. You take the inductive reactance, square it, add it to the resistance, squared, then take the square root, you get your impedance. Now, same thing, except it's going to be a little bit different looking. What if we have an RC circuit? Again, matters not whether they're parallel or series. Well, an RC circuit looks like this. R and X sub C. Again, if I have certain point, these make up, this becomes the line to that will become my impedance. And again, if I wanted to, I can plug numbers in, 3 and 4. This is nothing more than the same thing, Pythagorean theorem. This time though, X sub C squared plus R squared equals impedance. And if I plug the numbers in, I end up with 5 ohms again. If X sub C is 3 ohms, and my resistance is 4 ohms. Same thing. Only difference is this pointed down. That's going to become important when we put the two together. When we have a circuit that contains inductors or coils and capacitance or a capacitor and a resistor. Now when we have a circuit like that, where I have all 3 components, then it's going to look like this. Well, R over here, X sub L here, and X sub C here. Now, in a case like this, things start changing. If I have a certain amount of capacitor reactance, a certain amount of inductive reactance, and a certain amount of resistance, well, I can look at 2 vectors here, but one's got a negative going angle, goes this way, turning down. Remember, angles are generally positive going clockwise, but if you go counterclockwise, or going counterclockwise is positive, going clockwise, or going the other direction in the clockwise method will be negative. I would have to do some vector mathematics to figure that out. But there's a simpler way of doing this. These two are opposite each other. I can actually, since they're on a straight line here, I can actually just subtract them. So I can come up with a different graph, a resultant graph that'll look like this. Now it's going to look like this because I made X sub L larger. If X sub C was larger, it would just be reversed. But this time we'll call this X sub L minus X sub C. And this vector will be shorter by this amount. The resistance does not change. But this resultant does. Now by making use of that, the formula for it, the full formula for impedance is this: X sub L minus X sub C, that squared, plus R squared will equal C, or impedance. When you have an inductor, capacitor, and resistor in a circuit. Now the reason for these two going in opposite directions, and the reason why they subtract, goes back to what X sub L and X sub C is and how it's figured. Two pi FL 1 over 2 pi FC. Now remember, these two are not directly proportional, they're inversely proportional. So in other words, X sub C, the relationship, if F or C or both go up, this goes down. If these two go down, this goes up. Whereas this is directly proportional. If F or L or both go up, this goes up. If they go down, this goes down. That's what creates this. And this comes from the fact that how inductors and capacitors deal with an AC sine wave and the voltage and current. In inductors, when you have just an inductance in a circuit, then the voltage will lead the current by 90 degrees in phase. There's a phase difference of 90 degrees. So the voltage will peak out before the current starts flowing. Whereas in a capacitor, it's just the opposite. The current leads by 90 degrees the voltage. So the current peaks before the voltage actually starts flowing or developing. That's what creates this. That's what creates these math formulas for X sub L and X sub C. But the main thing I want you to realize is that when you have a circuit that has all three of these in it, an inductor, capacitor, and resistor, this is how you figure impedance. And all it is Pythagorean theorem of figuring a right triangle. And you take X sub L and always subtract X sub C. Once you got that, you square it, add that to the resistance squared, and then take the square root, gives you your impedance in ohms. Everything's in ohms. Now why even have impedance? And I want to touch on that real quick. This video is getting really long. The reason for impedance is when you look back at a DC circuit only, what you deal with is a voltage source, say a battery, and some load, which in this case will always be a resistor in DC. Simple circuit. I mean, no matter what combinations of resistors you have, you can work them out and bring them down to just a single resistance. And then you have just a single voltage source, single resistance. Use Ohm's law. You can find the current. You can find whatever you need to find in that circuit. That's real simple. Well, impedance literally works the same way as resistance, except in AC. I mean, you can use it in DC if you want, but in DC you only have just the resistor. These two have no effect on DC as far as any type of resistance or loading in there, other than the fact the coil will have a certain amount of DC resistance because the wire has resistance, and the capacitor just blocks, so it matters not. But in an AC circuit, I can use impedance the same way as I use resistance. So if I was looking at a circuit, let's look at a DC circuit. We have a battery. Let's say that battery goes to a resistor here, and a resistor here, and a resistor here. And I wanted to find the current in that circuit. Well, if this is R1, that's R2, and that's R3, then all I got to do is I've got to figure out this parallel resistance first, the total resistance. Well, R total in a parallel is 1 over R1 plus 1 over R2 plus 1 over R3. Once I find that, I can rewrite this circuit as a single resistance. We'll just call it RT, R total. Now I've got something real simple. I can have, whatever voltage here and whatever this works out. I can do Ohm's law, find the current, and I've solved my circuit. I know how much current's in it. I know what's going on. I can reapply that current back to here, find out the power across each one of these resistors, how much wattage drop they're going to have or dissipate, and so forth. Well, the same thing with impedance, except in this case I have a voltage source, AC, standard symbol, comes out, and I can draw impedance as a resistor, looking like a resistor, because that's all it is. It's AC resistance. So I can go like this, same style circuit, except in this case this is going to be Z1, Z2, and Z3. Again though, it works the same way as DC. Define the total Z, or total impedance, is the same thing. Z total equals 1 over Z1 plus 1 over Z2 plus 1 over Z3. Now these could be anything. They could be some filter circuits. They could be a tube in a circuit with its associated components to that circuit. Any number of things. But I can still break it down using the impedance, and finding the impedance the way we just showed. And I come down to this, I can figure this up, I end up with a circuit that looks like this. After I do the math, that I'll have Z total. Again, I can apply Ohm's law. I can find the current, I can take that current back to here and find various things going on there, wattage dissipation, power, the power and everything, and work out what's going to happen with that circuit in my design. That's why we use impedance. Now, in the next video that we'll be dealing with, we're going to look at impedance in a different way, or a little bit different way. We're going to look at, we have a tube, and we'll just draw a triode in here, but this tube comes across goes to a transformer, and that transformer goes out to a speaker. We're going to look at impedance matching. Matching this tube to that speaker through this transformer. How is that figured? And a little bit about the tube, selection of a power tube, and stuff. That's the other reason for the impedance. So that'll be on the next video. Not exactly sure, but it'll be out sometime. I'm hoping, well, let's see, this is Thursday. Probably by the weekend, I hope, if everything goes right, to be able to do that video and get it out to you guys, because I know there's been a lot of people wanting to know about that, and audio tubes and stuff. So we'll kind of go over that a little bit, and your impedance matching, and transformer selection, tube selection, a few things of this nature. So until the next time, I want to thank all of you for watching. Thank you for your comments. I know I haven't been doing a very good job getting back to them. I'm trying to answer some questions as much as I can. Still helping my kids with their remodel. It's a very large apartment and they're living in it, so that's really slowed things down. We spend more time moving stuff around than we do actually doing any work. And doing other things, so I'm hoping this winter things will kind of slow down and I can get back to just normal stuff. So but again, thank you for comments. A lot of your comments are you guys are too kind, and I appreciate all my new subscribers. I appreciate the old subscribers, the guys who's been with me from the beginning. You guys have stuck with me, so I really appreciate that. I appreciate all of you, and thank you so much. So until the next time, thanks for watching, and you guys have a great day.